Hello friends, welcome to Rajesh Data Engineering. In this video, I'm going to talk about one of the interesting concept of Spark architecture, that is internals of partition creation. This is one of the important topic and also it is mystery for most of the developers. Even though developers are working in Spark development for a long time, still they could not understand how partitions are being created within Spark environment. Even though they are aware of the concepts such as shuffling partition, repartition, coalesce, partition by, but still they don't understand how the partitions are created while pulling the data from external storage to Spark environment through Spark Reader. That is one of the mystery, and I'm going to uncover the concept in that internal mechanism. Today we are living in the big data world. For big data world, distributed parallel processing is the key. Coming to Spark architecture, that is working distributed parallel processing and also in memory. And that is the reason for Spark Lightning performance. I have already posted one video about Spark architecture. That is the the video number one in this channel. I have given all the internals of Spark architecture. I hope you have watched that video and you understood. It's very important to understand that concept. In case you haven't watched, I highly recommend to watch that video. So coming to big data world, we are working in the concept of distributed parallel in-memory processing. And for that processing, partition is the key. So basically, whenever we have to process huge amount of data, let's say terabytes or petabyte or exabytes, the data should be splitted in the form of partitions and it will be distributed across multiple nodes. Then multiple cores from multiple nodes can work in parallel to process the data. So this is how the big data is being processed and partition plays a key role in that aspect. So it's important for every developer or architect to understand the internal working mechanism of partition creation so that they can create high performance solutions. So in this video, I'm going to explain the internal concepts of partition creation. I have divided this video into two parts. One is how partitions are internally created while a data frame reader is connecting with external storage. What are the different components involved in that process? That is the first part of the video. And in the second part of the video, I'm going to explain how the number of partitions are decided while pulling the data from external storage. This is also one of the mystery for most of the developers. How the number of partitions are decided, even though they are aware of the concepts such as uh, default partition block size, that is 128 megabytes, and number of cores, no, that is a default parallelism. There are various parameters. Even the developers are aware of those concepts, but still they could not connect the dots to understand how the number of partitions are decided in a Spark environment. For example, whenever the partition size is set to 128 megabytes, but still we can see so many number of partitions created with 60 megabytes, 70 megabytes, 80 megabytes. But we used to wonder, we have set the maximum size as 128 megabytes, but still it is producing only 70 megabytes. Why two partitions of 70 megabytes cannot be combined? So these are the questions always we used to get in our mind while working in Spark. So at the end of this video, you will get answer for those questions and you will have better understanding of internal working mechanism of partition creation. Right. Let's get started. So first, I will explain what are the different components involved while creating the partition. So in order to understand how partitions are being created in Spark environment, it's very important to understand the high level processes of a Spark application. So let's say as a developer or one of the application that is contacting Spark engine to create a data frame. So let that client application that is giving the code like spark.reader, that is a Spark reader, then .csv, then it is giving some path. The path could be from Azure Data Lake Storage or HDFS location or even DBFS, Databricks file system. In order to connect Azure Data Lake Storage, the data lake storage should be mounted in the first place. So let us assume data lake storage is mounted, and in one of the location we are having certain CSV files. Now the data frame DF is created by reading the CSV file from Azure Data Lake Storage. So whenever this piece of code is submitted to Spark engine, what happens is the Spark context would be created, and first this particular code it will be submitted to driver. Driver will understand this code and it will optimize the code. It will split the entire process into multiple smaller tasks inside. Basically, it is creating lineage graph. In my previous architecture video, I have explained about lazy evaluation, transformation, actions. I hope you understood. So whenever we are submitting certain, will keep on building directed acyclic graph. That is nothing but lazy evaluation, lineage graph. Once we are calling action, then the entire code will be executed by calling the previous transformations. So whenever we are submitting some piece of code into driver, it will optimize the code, it will create a best execution plan, and it will divide the entire task into multiple smaller steps. Then it will submit those smaller steps into different executors. Executors are nothing but it's part of worker node. Worker node is logically divided into multiple executors. One worker node might contain one or more than one executors. Now whenever driver is receiving the program from the client application, then it is optimizing, then it is submitting one small portion of the work to worker node into this executor. Then executor will connect to the ADLS and it will start reading the data in parallel. So each executor will consist of number of cores. So each core will start consuming the data from external storage in parallel as long as the file is in splittable format. So for this parallel processing or parallel reading, the important concept is the file should be in the form of a splittable format. Even though the file is compressed, still few compressed file formats are splittable, like gzip. Those file formats are splittable, but coming to traditional zip or tar, these compressed formats are non-splittable. So let us assume we have kept our file in splittable format. Then worker nodes can connect to external storage. And then based on that, it can pull the data from ADLS and it will distribute the data across multiple executor in the form of partitions. So in order to summarize this workflow, driver is getting the application from one of the client application or one of the developer. Then it is optimizing the code. Then it is dividing that entire task into multiple smaller steps. Then each and every step will be given to executors. So all the executors or all the cores within the executor will start working in parallel. So let's say we have to connect to ADLS. For that it's one of the external storage. For that we need access key. So the storage account was already mounted. So the access key would be already part of driver. So driver will give those credentials to all the executors when it is submitting the piece of code. So through that credentials, all executors can establish the connection with the external storage and it can start processing the data. I hope you understood. Now I'm going to explain the worker node architecture. This is what I have already explained in my previous video, that is video number 1 in this channel. So just I want to give high level summary. What is worker node? Worker node is nothing but it's a part of cluster in Databricks or Spark. The cluster is nothing but combination of driver node and worker node. So worker node that is responsible to execute any piece of logic. A worker node that is logically divided into multiple executors. So in this case, here we can see executor 1, executor 2, and executor n. So each executor will consist of multiple cores. Let's say we are having one worker node which is having 12 cores and 12 GB RAM. Let us assume, for example, then what happens is, let's say we are going to divide that worker node into two executors. So it will be divided equally. 6 cores will go to one of the executor, another 6 cores will go to another executor. Similarly, the RAM that will also be splitted into two parts. And internally, we have to assign some cores for operating system, and also we have to assign some memory for operating system. So I didn't consider that in this example. Just for example, I'm giving 6 cores plus 6 GB RAM. But apart from that, we might have off keep memory also. And whenever some piece of code is given by driver to the executor, then all the cores within the executor that is responsible to pull the data from the external storage, and it will store those data in the form of partitions within on-keep memory. That is nothing but RAM memory. This is the worker node architecture. In case you want to get more clarity, please watch my previous video. Right now, Let us assume we are having 1 GB CSV file in ADLS location, and we are having only worker node. Within that, we are having only one executor. Now what happens is, let us assume we are having partition size that is decided as 128 megabytes. In this case, this 1 GB file, it will be divided logically, it will be divided into 8 pieces. So whenever we are dividing 1 GB data by 128, then it will come 8. So basically this 1 GB file will be logically divided into 8 pieces. Then while consuming the data from external storage into Spark environment, then it will come in the form of partition. Those logical divisions will be converted into physical partitions within executor on heap memory. I hope you understood that part. And coming to the relationship of files and the number of files versus number of executors. So in this example, what I have done is I have given only one executor, and we are also having only one file. But in real time, we might have only one executor, but we might have multiple files under a particular folder. And this one executor might consume all the files under the folder. Otherwise, we might have multiple executors, in the cluster. We are having multiple worker nodes, or within one worker node, we are having multiple executors. So multiple executors can work on one particular CSV file, which is splittable. Then it can distribute the file across the executors. Even multiple executors can access one single file. So the relationship is very simple. One executor can access multiple files, or multiple executors can access one file, or multiple executors can access multiple files. Hope you understood this concept as well. So here I have given another scenario where we are having only one CSV file, but we are having two executors in the worker node. So both executors will start consuming the data from the CSV file. Logically, it was divided, so all the cores within the executor can consume the data in parallel. So finally, 8 partitions got created. So it is uniformly distributed across executors, which means 4 partitions are going to executor 1, another 4 partitions are going to executor 2. I hope you understood. Now we are getting into important part. So in the previous slide, we have seen worker node, that is connecting with ADLS. Then the data is flowing from ADLS to worker node. But what is the internal mechanism? How worker node is connecting with ADLS? What is the component used for that? So the answer is, within Spark executors, there is a component called input format API. This is one of the important component within Spark architecture, and this component is responsible to connect with external storage and pull the data from external storage to Spark environment in the form of partitions. So it's important to understand what is input format API. So before understanding format API, let me summarize what happens when we submit application. So driver node in Spark is responsible for coordinating the overall execution of the Spark job, while the executors are responsible for actually processing the data. And the driver node sends a task to an executor. Then the executor uses the input format API to connect with external storage, such as HDFS, or it could be Amazon S3 bucket, or it could be Azure Data Lake Storage. So driver is passing the piece of logic to executor, and the executor is connecting to external storage with the help of input format API. So input format API is a programming interface which defines the logic for dividing the data in the external storage into logical splits and assigning them to different Spark worker nodes for parallel processing. The input format API also provides a way to specify how to read the data from various file formats such as CSV, Parquet, or Avro files. Because whenever we are working in Spark, we might be dealing with multiple different file formats such as Parquet, Avro, or CSV, even JSON. So whenever we have to read different file format, we should have some component which is responsible to give some logic to handle different file formats in a different way. For example, when we are reading CSV file, it should be treated in a different way. When we are reading JSON file, it should be treated in a different way, because the internal format is different for different file formats. So our component input format API should be able to understand CSV file, Parquet file, or JSON file. So in this input format API, this component is giving provision to handle different file formats differently. And this input format API, this is extension of Hadoop API. Originally, it was created in the Hadoop platform only, and currently it is leveraged for a Spark environment also. So Spark uses this Hadoop's input format API to support a wide variety of file formats and storage systems. I hope you understood what is input format API. Input format API is nothing but one of the component part of external executors, and that is responsible to integrate executors with external storage system. Right. Now, this input format API, this is one of the component, but internally it is having three different components. So let me show you what are the different components. First one is a file input format. This component is responsible to handle different file formats in a different way. Let's say CSV or Parquet Avro, we are having different file formats. How we have to handle those different file formats? That will be decided by this file input format. Then the second thing is input split. Input split, that is responsible to divide the data in the external storage logically. For example, we are having 1 GB data that should be logically divided into 8 pieces. So basically, this input split will access the external file, then logically it will split. Logical split means it will note down the address, starting memory address and the end memory address for each split. That split will be converted as a partition within Spark environment. So this input split that is happening within external storage itself. Right. And the third component is record reader. So this record reader, once input split is split as splitted the physical file into logical divisions, logical splits, then the record reader will start consuming the data from the external file system, and it will move the data to Spark executors in the form of partitions. These are the three major components. Let me dive into details for these components. The first one is file input format. File input format is nothing but one of the base class in Hadoop input format API, which is used in Apache Spark for reading data from files in Hadoop distributed file system or any other file system. It could be ADLS, S3, or even Google Cloud Storage. The file system could be anything. So basically, this base class, this component is responsible to deal the different file formats in different external storage systems. So input file format class is used as a base class for all file-based input format such as text or sequential file format Avro. And it provides methods to read and split input data from files into smaller partitions, which can then be processed in parallel across the Spark cluster. So this is the basic component in the input format API. Because this is actually establishing the connection between the external storage with the executor. Then based on that, input split component will split the data logically in the next step. Right. Coming to input split, as I told earlier, input split is a logical representation of a chunk of data that can be processed in parallel by single task in Spark job. And an input split defines a contiguous portion of an input data source, such as a file or Hadoop distributed file system block, and provides information about the location and size of the data. Which means, let's say we are having one Parquet file which is having 800 megabytes, just for example. Then this Spark engine has decided to split the data into 100 megabytes. So what happens is this 800 megabytes data will be splitted into 8 pieces logically. Then later, each split, this component, input split, this component will keep track of, all the splits. What is the starting address? What is the end address? And also, all the cores, all the executors can access the footer and header of the Parquet file, because a Parquet file will contain the metadata along with the data file. So the metadata that is common across all the executors or all the cores, but the input data that is logically divided into multiple parts, and each starting address and end address will be tracked. It will be tracked by input split. I hope you understood. And each split is associated with a specific location in the cluster where the data is stored. This information is used by Spark Task Scheduler to assign tasks to the nodes that are closest to the data they need to process. which can help minimize the network input output and improve performance. Yes, once the data is splitted, logically splitted, then task scheduler will start assigning the task to different cores, and that particular core or that executor, where it is residing. Based on that location, it will try to assign the storage location, which is closest to that particular worker node or to that executor, so that it can minimize the network input output, so that it can give better performance. And the number and the size of the split can vary depending on the size and distribution of the input data, as well as the configuration of input format used to read the data. Basically, we are having various Spark configuration parameters. Based on that, this input split size will be decided. So I will explain that part in the second part of this video, because that is the key for in deciding number of partitions while reading the data. I hope you understood what is input split. So here I have given one example. Let's say in ADLS location, we are having one input file, which is Parquet, which is of size of 800 megabytes. Let's say, this should be divided into maximum 128 megabytes. So what happens is, this component, this input split, this is part of input format API. Input format API, that is part of executor. So executor will connect to this storage using these components. Then it will start dividing the entire file into logical divisions. So basically, the first split will be, it will take 128 megabytes from this Parquet file. Then, the remaining, it will have 672 bytes will be there. Again, it is higher than 128. Again, it will be splitted. Then it will keep on splitting. Finally, the last piece, it will have only 32 megabytes. So basically, this 800 megabytes, this is being splitted into 7 parts. I hope you understood. So, but in this Parquet file, we will be having a header and footer, which will have data about this Parquet file, which means, the metadata, the schema, those information. Now, those information will be available for all the splits. And in order to split this Parquet file, the important condition is, this file, it could be Parquet, CSV, JSON, any file, that should be in splittable format. Which and coming to splittable, this CSV, JSON, these are splittable format. But in case these files are corrupted, then it cannot be splitted. And coming to compressed files, even this gzip, bzip, lc, these are splittable. But zip or tar, these are non-splittable files. So in case we are having non-splittable file, then this entire 800 megabytes will be consumed by only one core. This entire file will be considered as one logical piece. So that is going to hit the performance, because we are impacting the parallel processing. So it's very important to keep, very important to use splittable file formats and compression formats while working in big data, especially in Spark. I hope you understood. Moving to the next component within input format API, that is record reader. Once data is logically divided into multiple pieces, then this record reader will start consuming. So record reader is a component in the input format API that reads and deserializes individual records from an input split. So basically, this is transporting the data from external file system to Spark environment. So this is the entry point where data is flowing from external file system to Spark in memory. And this record reader, that is responsible for reading and parsing each individual record from the input split and converting them into a format that can be processed by Spark. And how this is actually transporting the data into a Spark environment. So that is explained in this step. The record reader typically reads data from a file or database table and converting it into key value pairs. So in case of reading a CSV file, the record reader would read each line of a file and parse it and convert it into tuple representing data in that line. So basically, any data file that we are reading, it will be converted as key value pair. So it will maintain one key. The value will be one record from the file. It could be CSV, Parquet, whatever it is. It will convert that physical file located in the external storage. It will convert that key value pairs, and it will export the data from external storage to Spark environment in the form of key value pairs. Once the record reader has processed all the records in the input split, it returns a set of key value pairs where the key is a typically unique identifier for the record, and the value is the actual data that Spark will process. I hope you understood. These are the major components involved in creating partitions. So this is how partitions are creating partitions are getting created internally within Spark environment. Whenever we are giving some command like df equal to spark dot read dot parquet, then giving path. Whenever we are submitting some such piece of code to Spark engine to cluster, what happens is this is internally happening. So basically, driver is accepting that code, it is optimizing, then it is dividing that into multiple smaller tasks. Then each task is given to executors. Then executor will establish a connection with external storage with the help of input format API. Within input format API, we are having three components. First one is file format API that is responsible to handle different files in a different way. And the second one is input split that is responsible to split the actual physical file into multiple logical chunks. And the third one is a record reader that is responsible to transport each splitted input splitted data into Spark in the form of partitions. I hope you understood the concepts. Now we are moving to the second part of the video. In this video, I'm going to explain how the number of partitions are decided while creating. Now you understood how partitions are being created within Spark environment. Now the second part, you will understand how the number of partitions are decided. Right. Coming to Spark environment, in order to decide the number of partitions, there are three major parameters involved. The first one is Spark default parallelism. This is one of the important Spark configuration, and the default value would be total CPU cores count. Let's say we are having one worker node within that one executor which is having 10 cores, which means this parameter spark.default.parallelism that will be done. But this is custom, we can customize that. We can change it to 20, 30. We can change the value, but by default, the value would be number of cores. And the second important parameter is spark.sql.files max partition bytes. Now this is deciding the block size of each partition. By default, it would be 128 megabytes. Again, depending on the use case, we can change this one. And the third parameter is spark.sql.files.open cost in bytes. That is by default 4 megabytes. Again, this is changeable. But probably you might have understood, or you might have come across these parameters: parallelism and maximum partition bytes. But this is quite new, open cost in bytes. But this is also playing important role in deciding the number of partitions in Spark environment. So what is open cost in bytes? So in my previous example, I told we are having 800 megabytes of Parquet file, which is logically divided into 8 pieces. Now after dividing those pieces, those file into multiple pieces, now in case we have to pack two logical divisions into single file, then whenever we have to pack two different files into one partition, then we have to use 4 megabytes as a overhead, processing overhead, because this 4 megabytes will be used as a buffer to merge two different files into one partition. Let's say we are having just 20 megabytes JSON file and one more 30 megabytes JSON file. Now we have to combine these two and convert into one single partition. Then in that process, what happens is the first file 20 megabytes will be taken, and 4 megabytes of this open cost in bytes will be used. Then on top of that, the second file 30 megabytes JSON file will be added. So overall, it will have 54 megabytes. So this 4 megabytes, this is nothing but process overhead or buffer memory that is needed to pack multiple files into single partition. Right. These are the three major parameters which are used to define the partition count in Spark environment. Right. In order to understand how the number of partitions are being decided within a Spark environment, we need to understand two different formulas. One is bytes per core. The second one is max split byte. We have to understand two different parameters. I will explain that. The first one is bytes per core. What is bytes per core? So to understand bytes per core, let's say we are having 10 cores in our worker node and we are having 1 GB file. Then what happens is this 1 GB file will be divided by number of cores. So it will come approximately 100 megabytes, which means each core within the cluster can process 100 megabytes approximately. That is the calculation of this bytes per core. Bytes per core is nothing but now whenever we are going to distribute the total number of files across available number of cores or available executors, how it can be distributed uniformly. This is one of the rough estimate. Based on this estimate, still we have one more formula. Based on that, the number of partitions will be decided. First, let us understand what is bytes per core. This is nothing but bytes per core is a parameter that defines the amount of memory allocated per core in a Spark worker node to use for its operations, such as reading, processing, caching, and shuffling the data. And the formula is bytes per core equal to sum of sizes of all data files plus count of files multiplied by open constant files. Let's say we are having 20 files, and in order to pack those 20 files, we would need 4 megabytes for each file. So 20 files multiplied by 4, then divided by default parallelism, that is by default number of cores. So this is the formula for bytes per core. Right. The second parameter is max split bytes. So max split byte is nothing but this is the actually partition size. So in our system, we are having thousands of files. Let us assume in our storage we are having thousands of files under a folder. Now we have to create a data frame by reading all the thousands of files. Then in order to convert those thousands of files into physical partitions within Spark environment, this parameter is important. Now based on this value, the final partition size will be decided. So what is this max split size? So this is one of the parameter that determines the maximum size in bytes of a data block that can be split during data reading. So the formula is it's a minimum of maximum partition bytes comma bytes per core. So in our previous slide, we have seen the formula of bytes per core. So this will be calculated in the first step by Spark engine. Once bytes per core is calculated, then the value maximum partition bytes. This is one of the Spark parameter. So by default it would be 128 megabytes. Let us assume by default we are giving 128 megabytes and bytes per core that is coming as 200 megabytes. Then this max split bytes it will be considered as a minimum value of these two. So here 128 megabytes, here 200 megabytes. So which is minimum 128 megabytes. Then 128 megabytes will be decided as a partition size in that particular data frame reader. And let us assume we are having maximum partition size as 128 megabytes, but the calculated bytes per core that is coming as 80. Then the minimum of these two, 128 comma 80. 80 is the minimum. Then 80 will be the partition size for that particular data frame reader. I hope you understood. So first we need to calculate bytes per core. Basically that is calculated based on those important three parameters. Once that is calculated, then max split bytes is being calculated using this formula. So based on this value, let's say in 800 megabytes we have calculated, and let's say the maximum split size is 100. Then what happens is it will start logically splitting the Parquet file into 100 megabytes. Then executor can consume those 100 byte logical divisions in parallel. That will be converted as physical partitions within Spark environment. Hope you understood. Right. So I'm going to give you some scenario. Let us assume one of the developer, in the development environment, is passing a Spark application to the cluster. So it is spark.read.csv. Then one of the sales data. Within that, basically we are having three CSV files under sales folder. We are having one sales folder under ADLS location. Within that folder, we are having three files. Sales, this is for each month: 2023-01, 2023-02, and 2023-03. Now these are different in sizes. The first file that is 100 megabytes, second one is 500 megabytes, third one is 700 megabytes. So now we have to create a data frame DF by reading all the files under this folder. So whenever this particular code is given to cluster, then driver is responsible to optimize, and it will create multiple tasks, and task will be submitted to executors. So let us assume in this case, we are having our executor, there are 4 cores. We are having 4 number of cores. And let us go with the default parameters. We are not customizing any of the Spark parameter. So the default parallelism, that is 4, because we are having only 4 cores. So by default, the parallelism would be total CPU core count. Here we are having 4 cores, so this parameter will be 4. And the second parameter, maximum partition bytes, that is 128 megabytes. I will go with the same value. And the third one, open cost in bytes, that also I'm going with the default value 4 megabytes. So whenever we are submitting this Spark application to the cluster, which will contact ADLS. Within ADLS, we are having 3 files. Now let us try to understand, how the number of partitions will be decided for this use case. So for this use case, first of all, we need to calculate. The Spark engine will start calculating bytes per core, which is nothing but it's a sum of all the files that is distributed across number of cores. It's approximate calculation. So the formula is size of sum of sizes of all data files plus count of files multiplied by open cost in bytes divided by default parallelism. So coming to this sum of sizes of all data files, here we are having 100, 500, 700. So whenever we are performing addition, it will be 1300 megabytes. And count of files, that is 3 files. We are having 3 files. And open cost in bytes, that is 4. So 3 multiplied by 4, that is 12 megabytes. So basically we have to add these two, sum of this value with count of files multiplied by open cost in bytes, that is coming around 1312. And that can be divided by default parallelism, which is 4. Then based on this values, we are getting bytes per core as 328 megabytes in this use case. Now the first step, Spark engine will calculate bytes per core. That is completed now. Now the second step, we have to calculate max split bytes. So in this case, max partition bytes, it's 128. So the formula for max split bytes, that is minimum of this maximum partition bytes and the bytes per core. So maximum partition bytes, which is 128, and the bytes per core, which we calculated just now, that is 328. So the minimum of these two value, that is 128. So for this particular data frame reader, in this example, we have given one of the Spark calculation. We are submitting one Spark application to the Spark cluster. So finally, the Spark engine has decided to create partitions of maximum size of 128 megabytes. Hope you understood. Now, once that value is decided, 128 megabytes, that is what we calculated. Now the input split, that is one of the component in input format API. It will start splitting the files in the external storage logically. So the first file, it's already 128 megabytes, but it can be splitted up to 128 megabytes, but it is already only 100, so which is lesser than that. So there is no point in splitting this file into multiple pieces. So it will go as it is. And coming to this 500 megabytes, this is more than 128 megabytes. So that's the reason it will be divided into 128 megabytes. Then the last remaining part, which will have only 116 megabytes. So this 500 megabytes, this will be logically divided into 4 pieces. Okay, 128 pieces, and the last piece, it will be 116, because now 500 megabytes, the last piece will contain only 116. And coming to the last file, 700 megabytes, again, this is bigger than 128 megabytes, and it can be splittable. It can be splitted. So it is dividing 5 128 megabytes, and the final piece, it will have only 44 megabytes. So basically this is divided into 6 pieces. So the input split, it is splitting all the files within the Azure data lake storage, and finally it has come to this conclusion. The first file, that is not splitted, it is going as it is, because this is already less than the maximum partition size, that is 128 megabytes. And coming to this 500 megabytes, it is splitted into, logically splitted into 4 pieces. And this 700 megabytes, that is also logically splitted into 6 pieces. Now The second, so basically, the logical division, it will be like this, 100 megabytes, it is going as it is. And these four files, basically it will take the starting address and the end address for each file. Okay, within this 500 megabytes, basically this is this is being stored in one of the disk address. So basically it will take the address of starting byte and the end of the byte also. So basically this is divided into these many pieces. So here we are having 1 plus 4 plus 6, so 11 pieces we are having. Now in the next step, that record reader will start packing all these files, all these logical divisions into partitions. So while doing that, it will start it will try to combine some files in case it can be combined, so that it cannot exceed the maximum size. So for example, in this case, first of all, this file 100 megabytes, that is less than 128 megabytes. Still, 28 megabytes can be added to this split. Then it will check, if you are having any files which is less than 28 megabytes, so that it can be added. But we don't have anything, because in this particular file, the smallest one is 116. But if you are going to add this 116 with 100, it will be 216. It will exceed the maximum partition size of 128. So it cannot be combined with this one. And coming to this one, the smallest one is 44. Even this 44 cannot be merged with this 100, because it will become 144, which is again greater than 128 megabytes. So this 100 megabytes will be considered as single partition, and it will be transported to Spark environment as it is. And coming to this 500, again, these files, it will be it will start checking it is having the maximum bytes or not. Yes, 128 megabyte. No, these are maximum. And coming to the last one, 116, it can be combined with any other file, so that it can be uh, maximum of 128. But again, we don't have any other smaller file to combine with this one. So even this 128 116 will go as one separate partition. Similarly, coming to this 44, we don't have any other data file to combine with this one, so that we can increase the size within 128 megabytes. We don't have any other file. So even this 44 will be considered as one of the single partition in Spark environment. So whenever this particular data frame is created, so that data frame will contain 11 partition, and the first partition will contain 100 megabytes, and few other partitions will have 128 megabytes, and one of the partition will contain 116, and one more partition will have 44 megabytes. So whenever you are creating data frame for this particular use case, now this is what you will see within Spark UI, within Spark memory. So you might wonder, why this is having separate files, 100, 44, 116. But this is the reason, how internally this is working, how it is deciding the number of partition. So overall, it is creating 11 partition for this use case. I hope you understood how the number of partitions got decided in this use case. Now I'm going to explain the process of partition packing. What is partition packing? So let's say in our Azure Data Lake storage, we are having five CSV files. Each one of the file is having 63 megabytes. In real time, we are not going to have files of same size, but just for this explanation, just for this example, I am considering we are having five files, all are of 63 megabytes. Now let us assume our Spark engine has calculated maximum split bytes, that is 128 megabytes, which means one partition can be up to 128 megabytes. So that is a formula. Now Spark engine will start combining multiple files in order to create a partition. First of all, it will try to, this is 63, that is already less than 128 megabytes. So it will try to add one more file along with that in order to create maximum partition size of 128 megabytes. But here, whenever we are adding 63 megabytes with another 63 megabytes, what happens is, the maximum size will be 126, which is coming less than 128. We might calculate in that way, but that is not the right calculation. Why? Because whenever we have to combine multiple files, Spark engine needs some buffer size, that is open cast in bytes, that is 4 megabytes. So in this example, Spark engine will take the first file, that is 63 megabytes. Then in order to combine another file, it will start adding the overhead or buffer memory, that is 4 megabytes. Then it will start adding the second file, 63. Then the combination of these three files, in order to combine these two files, we need 130 megabytes. so which is greater than 128 megabytes. So in this case, we cannot combine two different files. Now this 63 file cannot be combined with anything. So in this case, 63 megabytes file will go as one single partition, even though the maximum partition size for this scenario is calculated as 128 megabytes. But still, this 63 megabytes file cannot be merged with another file in order to create single partition. So each file will create single partition within Spark environment. So for this use case, overall, it will create 5 partitions. We are having five files. It cannot be merged with another file. So each file will create separate partition. So overall, we will have 5 different partitions for this scenario. This is partition packing. And let me give a different scenario for this partition packing now. One simple minor change. Okay, instead of 63 megabytes, I'm going to keep 62 megabytes. In now, what happens is, we can assume the maximum split size same 128 megabytes and open cost in bytes, that is 4 megabytes. Now the Spark engine will look at the first file 63 megabytes, that is less than 128 megabytes. Now it will try to add any of the other files. Then it will start trying to add the second file. Then the first file 62 megabytes. In order to add the second file, it will add 4 megabytes open cost in bytes. Then after that, it will add the second file 62 megabytes. Now whenever we are calculating this, this is 124, then plus 4 128. That is lesser than or equal to this 128 megabyte, our partition. Then in this use case, two files can be combined into single partition. So in this use case, the first two files will be combined to create a single partition. Another two files will be created to create another second partition. And the third one, it does not have any more files to combine, so it will go as it is. So overall, in this use case, 3 partitions will be created. I hope you understood the difference. Just in the previous example, we had 63 megabytes, which created 5 partitions. But in the next example, we are having very minor change in the file size. But we can see the difference in number of partitions. It's one of the simple example, so that's the reason it has. We can see the difference of 5 partitions to 3 partition. But we are having thousands of files, then we can see very huge difference in number of partitions for both use cases. I hope you understood. So this is overall process, how partitions are created and how number of partitions are being decided within Spark environment. For that, we are having default parameters. Then we need to calculate bytes per core. Based on that, we have to calculate maximum split bytes. Then in order to pack two different files, partition packing, it will take open cost in bytes. These are the major parameters involved while deciding number of partitions in Spark reading. I hope you understood the entire process. Now I'm going to give you different scenarios. Based on that, you can understand, you can get thorough understanding, how Spark engine works internally. So the first scenario, we can go with the default parallelism. That is, we are having 8 cores. So the parallelism, that is 8, and maximum partition bytes 128 megabytes, and open cost in bytes, that is 4. Let us assume in the external storage we are having 30 Parquet files. Each is of 63 megabytes. So for this scenario, first Spark engine will calculate bytes per core. So let us also calculate that. So basically we are having 30 files multiplied by 30 bytes per core. We have to calculate sum of sizes of all data files, which means we are having 30 files multiplied by 63. Then after that, count of files multiplied by open cost in. So count of files, that is 30, and open cost in bytes, that is 4. So 30 multiplied by 4 divided by default parallelism, that is 8. So whenever I am going to apply this formula, I will get bytes per core approximately 251 megabytes. So the first step, Spark engine will internally calculate this value. So this is coming as 251. Then the second step, it will start calculating maximum split bytes. So for that, it will take the minimum value of this maximum partition bytes and bytes per core. So maximum partition bytes, that is 128, that is coming from the default parameter, and bytes per core that got calculated just now 251. So the minimum of these two value 128. So in this case, the maximum split size, that is 128 megabytes. Now Spark has decided, I can create a partition with maximum size of 128 megabytes. Now we are having 63 MP files, okay, 63 megabytes. So Spark engine first, it will add the first file. Then second file, it will in order to add the second file, it has to add open cost in bytes, then that is more 4 megabytes, then adding the second file. So overall it is coming to 130 megabytes. So in this use case, two files cannot be merged. So each file will create a single partition. So as a result, two files cannot be packed together to create a partition. So each file will be created as a single partition, which result 30 partitions for this scenario, because we are having 30 files, each of 63 megabyte. So each partition will create separate partition. So we will have 30 partitions in Spark environment for this use case. Moving to the second use case, let us assume we are having a number of cores that is 10, that is a default parameter. We are having maximum partition bytes 128 as it is, and open costing bytes we are keeping 4 megabytes. Now let us assume we are having 40 Parquet files, each of 15 megabytes only. Now for this use case, first Spark engine will start calculating bytes per core. So we are having 40 files multiplied by 15, 40 multiplied by 15, and the number of files multiplied by 4. So we are having 40 files multiplied by open cost in bytes. So divided by number of cores, that is 10. So we are getting bytes per core as 76 megabyte. Now in order to create max split bytes, the maximum partition bytes, that is 128, and the calculated bytes per core, that is 76, we have to consider the minimum of these two. In this case it is 76. So Spark engine has decided to get partition with maximum size of 76 megabytes. Now in this case, Spark engine will consider the first file, that is 15 megabytes. Then it will add open cost in bytes 4 megabyte. Then it will start adding the second file 15 megabytes. Now it will check, it is coming 34, but still that is very lesser than 76. Then it will try to add the one more file. For that it has to add open cost in bytes 4 megabytes. Then it will add one more file, third file 15 megabytes. Again this will come around 54 bytes only. 50 54 megabytes, again it is lesser than 76. Then it will try to add one more file. For that, first it will add 4 megabytes open cost in bytes, then the fourth file 15 megabytes, which is coming around 72, which is closer to 76. Now we cannot add one more file, fifth file we cannot add, because it will exceed 76 megabyte. So Spark engine will started packing. It will out of these 40 files, every 4 files will be packed together to create a partition of maximum size 76. So in this case, 4 files will create single partition. So 40 files will create 10 partition. So for this particular use case, whenever we are reading, we are creating a data frame out of these files, then in Spark memory we can see 10 partitions, each of having 32 megabytes. I hope you understood. Coming to the last scenario, let us assume we are having number of cores 32, and the remaining other two parameters I'm not changing. Max partition bytes 128 megabytes and open costing bytes 4 megabytes. And Parquet file, let's say we are having 600 files, and each having 30 megabytes. So for this use case, Spark engine will calculate bytes per core. So that is 600 multiplied by 30. Then after that, number of files multiplied by open cost in bytes, that is divided by number of cores 32. So it is coming closer to 637 megabytes. Now Spark engine will calculate a maximum split bytes, that is nothing but minimum of this max partition bytes and 637 bytes per core. So out of these two value, 128 megabytes, that is the minimum one. So it will consider 128 megabytes. Then Spark engine decides to go with partitions of maximum size 128 megabytes. In order to create the partitions, we are having Parquet file which is less in size. So it will start packing two files first. For that, it will add the first file, then it will take open cost in bytes, then the second file is being added. So overall, it is coming to 64 only, but we can still pack few more files, because the split size is 128. Then it will start adding another open cost in bytes. Then again, it will add third file. So overall, now it is going to be 98 megabytes. So that is closer to this 128 megabytes, but still we have close to 30 bytes, but 30 megabytes. But if I'm going to add 30 megabytes, what happens is now I have to add open cost in bytes also plus 4. So overall, it will be 132 megabytes in case I have to add my fourth file. So that's the reason Spark Engine will consider only 3 files. It will start packing only 3 files, which is of 92 megabytes. So in this case, each 3 files will create one single partition. So we are having overall 600 files. So it will create 200 partitions overall. So each 3 files will be packed together to create a partition. As a result, 600 files will create 200 partitions. I hope you understood. I have given different scenarios. How partitions are being created from the external storage system to Spark environment, and also how the number of partitions are being decided while reading the data from external system into Spark engine. I have given all the components involved in this process and also all the calculations. I have given many use cases also, so that you can get better understanding. So this is the overall complete calculation. I hope you understood the process. You enjoyed this video. If you like the content of this video, please like and comment in the channel. Please subscribe this channel and don't forget to click on the bell button to get latest videos on Databricks. Thank you.